So hello everyone, we'll be discussing section 5.2, which is the tensile test in today's class, and through that test we will be learning about many new terms about the behavior of a material, and parts of this will sort of overlap with what you learn in your course in material science. Okay, there's no escaping that fact. Okay, so we begin with your textbook, which says that in common with all branches of science, we wish to develop a theory which will allow us to predict behavior in a general situation from the results of an experiment made in a very simple situation. Okay, so when they say that you want to predict behavior in a general situation, is like if you apply so much of load, what should be the stresses which develop? Okay, if the stresses have developed so much, whether it's enough to permanently deform it, whether it elastically deforms it, whether it will fracture it, and so on. So this is what we mean by the behavior which we would want to predict using this theory. So, and we want a experiment which is made simple, and the tensile test is that experiment. So the most simple loading situation we can imagine is one in which a relatively slender member is pulled in the direction of its axis. Okay, so you have a slender member. Remember what this was? The length is much longer than the other dimensions. Okay? And this is being pulled in the direction of its axis. So this is called a tensile test. Okay, you can try to pull your pen, you can try to pull a piece of string. So those are all tensile tests. Okay, so our aim is to use tensile test data to formulate quantitative stress-strain relations, which when incorporated with equilibrium and compatible requirements will produce theoretical predictions in agreement with experimental results. Okay, so using this tensile test, you want to find a relation between stress and strain. This is what you want to do right now. Okay, so remember, the objective of this chapter was to find the relationship between stress and strain, and obviously at a point, because stress and strain is dependent at a particular point, hence that relationship also is valid at that particular point in the most general case. Okay, but we will consider a simpler case in our description. Okay, so the idea is that you should be able to predict what experiments give out after this, and after this developing this relationship. So to perform a tensile test, a piece of material is cut in the form of a cylindrical test specimen. Okay, this is your cylindrical test specimen. You have to, so this is the thing, your material, the solid which you are given to you may not actually be of a slender cylindrical shape, but you have to cut out a part of it which is slender and which is cylindrical in shape. Okay, this is the most common way. The ends are moved apart by a testing machine which indicates the load required at each stage. So this is the load which is being applied, and these two ends are pulled apart in the direction shown by a testing machine, or in short UTM, which is called a universal testing machine. Perhaps it can do other tests than this. So this is very commonly used, and if you were doing some practical experiment, I think in material science or in an experimental mechanics course, most likely you would do a test like this. If not, I would request you to please see a video of a UTM machine. Okay, so you can just pause and see a video of a UTM machine. Any UTM machine would be okay. Okay, so the ends are moved apart by a testing machine which indicates the load required at each stage. So at every stage of this elongation or this, you will get the force which is acting over here. Okay, this is what this machine gives you, and this is not some very fancy machine. I mean, if you principally look at it, it is just like a weighing machine or the machine which you use to say measure the weight of vegetables and things like that. So it just gives you a force, right? at the end of the day. Okay, but obviously to a precision which is required for science and engineering, and the accuracy as well. So the ends are moved, the elongation and the lateral contraction are also noted as the test proceeds. Okay, so you want to see how much this length is increasing as the test is proceeding, in the sense when you try to pull it by this force, and the force will keep on increasing, and at every stage you will notice how much this length has increased. This is done using this gauge, which has one fixed end over here, the movable end over here, and it will measure this dimension. Similarly, you would also want to measure how much is the lateral contraction. I mean, if the length of this is increasing, the width will decrease. So you have another gauge which measures the lateral contraction in this at each stage of your test. Okay, so you start with a zero load, and then you keep on increasing the load gradually, and keep on taking these readings, and what is the force at that stage. Now, since we expect thicker specimens to carry higher loads and longer ones to stretch farther, as was indicated in one of your earlier figures. I mean, if you remember figure 2.4, if I'm guessing, let me see. So we had 3 bars of different lengths and areas, and we were trying to pull it. Figure 2.5, I think. Yeah, figure 2.5 in the textbook. So in your text, I think it is wrongly given as 2.4. It should be 2.5. And in this figure, you had this 3 bars, L1 and of area A1, and then L2 of area A2, and L3 of area A3, and you were trying to pull it. So that is the idea which we had seen there. So all the graphs were different from each other, starting from 0, and the longer ones were stretching further. We want to convert the results of such tests from load and elongation to stress and strain. Okay, so that it's not dependent on the dimensions of the specimen. So that is the reason we want to convert this load versus elongation into stress versus strain. So that's what we'll be doing right now. Now let's take the x, y and z axis as is shown in this figure 5.3. The x, y, z axis is shown, the origin is already indicated, and one of the things to notice is that x is coincident with the axis of this specimen. Okay, so it is the axis of the x is also coinciding with the axis. Now the only component of the stress present is the normal stress component, which is sigma x. Because of its slender structure, the only component which is present is sigma x, and it is found by dividing the load with the cross sectional area. So not a big deal. Okay, you would just find the load at a given stage from this machine. That machine will give you the load. This is what the machine gives. It gives you the load, the force, and all you have to do is divide it by the cross sectional area of this specimen. Okay, now let's come to the strain. The component of strain which is reported in the tensile test is the axial normal component. Okay, and to obtain this you have two gauge marks which can be seen over here. Let's see this figure 5.4. Okay, so you have the original position of the gauge marks. This is the fixed position. I should not mark. Okay, so this is the original position of the gauge mark, and this is the one which is original, the dot which you see over here. That is the original position, and then this particular one is taken as your reference point. Okay, meaning you will measure the displacement of this point with respect to this one. So that's why this is called the reference point. And taking the lower gauge mark as a point of zero displacement, the displacement vectors of various points on the specimen will be as shown in figure 5.4. Okay, so this particular point has now moved to this new location and it shows the displacement. You have other points as well. I mean, all the points on this specimen below this will actually move downwards. All the points above this will move upwards. Okay, so this is like a general behavior which you would see. The point is that all of the points will get displaced. Okay, so any point will get displaced on this. So this is sort of an indication of how the displacements of the points will happen, and you consider only 2 points, so the gauge marks are made over here. Okay, now finally after, I mean, as you keep on doing this test, say the separation between them was L, now it has become delta L finally. Okay, and with once you have stopped increasing the load, and that is what is shown over here. So L plus delta L is the final separation between two gauge points. So the displacements, for example, if they vary uniformly over the gauge length L, so this is called the gauge length L. Okay, and this is sort of your region of investigation. So you don't like consider points outside this region, so you don't consider this point, for example. Okay, that is too close to the boundary. You want to be as away from the boundary as you can. So if the displacements vary uniformly over the gauge length, you may write u is equal to capital X by L into delta L. Okay, so I'm sorry, this should not be capital X, this is a small x. So you can make that correction in your equation. Okay, so this is what, so this is the logic, that if the gauge length L has displaced by delta L, the gauge length 1 will get displaced by delta L by L, and similarly the gauge length of X will get displaced by delta L by X. So this is where this displacement is coming up. Okay, so it's just like applying the unitary methods which you may have learned in your earlier education. It's the exact same idea. Okay, so once you have the displacements at any given point X, okay, at any given points X on this, from this place, any given point X, and X, as you know, can go from 0 to L. Okay, you apply this and the uniform displacement is assumed. This assumption must be very carefully noted. Uniform displacement. What does uniform displacement mean? The displacement at this point and this point and this point will all be of the same type. Okay, it's not a non-uniform displacement. We have already gone through this uniform and non-uniform. Remember, there was this rubber cylinder which was pushed from both sides in a uniform and a non-uniform way. So we are coming with the same idea. Anyways, for a uniform, for the displacement which are uniformly varying, so u of x, so to say, so this is a variation. Let me just write out like this. Okay, u of x is equal to this. So at the position L, the displacement will be delta L. At the position 0, the displacement will be 0. Okay, that is what was assumed, that you take the lower gauge point as a mark of 0 displacement. So you see the language which is given. Okay, once the strains are small, you can use the normal strain and find the normal strain as dou u by dou x, and that would be delta L by L. Okay, so that's how you have found the strain. Sigma x was, as we had said, was just the force divided by the cross-sectional area. And what this does is that, if you remember the figure 2.5 and perhaps the figure after that, it helps you get independent of the dimensions. So this stress versus strain, which will help us achieve the same purpose. So it will not depend what would be the length or the area of the specimen which you have carved out. Any area, length or any dimension should give you the same relationship between stress and strain at a point, and that's what we are trying to achieve. Okay. Now the results of room temperature tests on a variety of materials are shown in figure 5.5. Okay, so have a look at this figure 5.5. Okay, let me just enlarge it slightly. Okay, so we'll study this diagram very carefully. Now you already know what strain is, and this is the same tensile test experiment which is done. Okay, so let's see what this figure means. These tests were carried out to strains of only a few percentage, meaning the strains were small. Okay, that's the important part. And you can see that the value of strains are so small over here. You can see that, right? 0.002, 0.004, this is 0.004, this is 0.008, and so on. So it's a very small percentage of strain. Okay, and so like if you multiply them by 100, it would still be what, 0.2 and 0.4%. That's like very small strains. And then even the worst ones are like 1.8% and 2.2% and so on. Okay, so you have taken three materials. One was steel, the other was aluminum, and the third was aluminum alloy. So let's see what they are. So 1020HR, okay, 1020CR, and this is the alloy 4130HT, heat treatment, oil quenched from 870 degree, tempered at 315 degrees Celsius. So you have three separate materials, and again in your material science course you may learn about hot rolling and cold rolling and what those terms are, and what is quenching, what is tempering. So you don't have to worry about the manufacturing process as of yet, but the whole point is the way you make your steel, which is a mixture of iron and carbon, will define the material properties. Okay, so as of now you please take them as three separate sort of figures. Okay, three separate materials as such. Okay, and so so 10, it is the note is made in your book. This 1020 cold rolled steel is very similar, is a close approximation to the behavior of steel which we had seen in the paper clips in the last class. Okay, so this is quite close to that. Now there are a number of features which many of the stress strain curves of this have in common. First of all, look at this diagram. Okay, and you will notice that there is a region where stress is very nearly proportional to strain. Okay, there is a region for all three curves. These are the three stress versus strain behaviors, and clearly they are independent of now your length and cross sectional area. Okay, because you have written a stress versus strain. If you were writing a load versus displacement, you would get a different curve based on what load and what area you would get. Okay, fine. So there's a region where the stress is proportional to the strain. Let me show you that region. This region for 4130HT is heat treatment is this one. Do you see that the stress is proportional, very nearly proportional to the strain? So sigma x is proportional to strain. Similarly, in the 1020 cold rolled, this is the region where it's almost proportional. I mean between this zero strain and say this strain, okay, more or less. And similarly for this 1020 HR, this is the region, okay, where the stress is linearly related to strain, proportional to the strain, approximately, okay, very nearly. So now you have a term called the proportional limit. Again, a word in the italics in your textbook. Proportional limit is defined as the greatest stress for which the stress is still proportional to the strain. Okay, so it is the maximum value of stress at which the stress is still proportional to the strain. That is what a proportional limit is. So, proportional limit. Okay, the elastic limit, this is another term which is italized, is defined as the greatest stress which can be applied without resulting in any permanent strain on release of stress. The definitions are everything over here. You can't play or change or modify the definitions. So the elastic limit is defined as the maximum stress which can be applied without resulting in any permanent strain upon release of the stress. So you have this slender specimen, you increase the stress from 0, okay, actually you increase the force, but stress is the parameter which we are using to understand or analyze this test. So you increase the stress from 0, you keep on increasing, and then there is this maximum value of stress, after which if you release this, it will not go back to 0, the deformation will not go back to 0. Okay, so that should be the maximum stress at which there will not be a permanent strain on the release of the stress. Okay, so these are the three these are the common factors which you have learned about, two common factors, and we'll keep on coming back and forth in these diagrams. Okay, so this is the steels which you have. This is the aluminum. Okay, and if you have a 5.5 C, you have it for the glass. Okay, then you have for the gray cast iron in tension and in compression, and then finally you would have for polymethyl methacrylate. Okay, so you have all these graphs, and we'll gradually come and discuss these one by one, so that when we can define the terms which we need for our knowledge. So let's first go back to figure 5.6, not go back, go ahead to figure 5.6. So figure 5.6 illustrates 5.6a to start with. Okay, so this is, as you see, a stress versus strain graph. It's for a general solid, and it illustrates the loading and unloading behavior of a material which is elastic at stresses greater than the proportional limit. Remember, there were two limits, proportional limit and elastic limit. For these materials, if the which is elastic at stresses greater than the proportional limit. So for these materials, the proportional elastic for these materials, if the stress is increased beyond the elastic limit and removed, the stress strain curve has the shape shown in figure this. So if you have say an elastic material, if you load it, if see, the stress will keep on increasing from 0, so the arrow shows the loading part. Okay, and you keep on increasing the load, and if you stop and release it, well, it will come back to 0, the strain will be 0. Okay, then you start again slowly increasing, come back to this point, release again, it will come back to 0. Okay, so this is what is shown in this particular diagram, that this you are applying the stress within the elastic limit. Okay, so the maximum stress which you have gone is lower than your elastic limit, and in this case when you release the load, it will come back and it will not cause a permanent strain. You see, it will come back on unloading and it will get to zero case. But that is not always the case. I mean, if you look at 5.6, which is for a plastic behavior or a plastic material, you increase the load, okay, and it goes all the way up, and when you unload it, it comes back to this strain which is not zero. So you have clearly bypassed the elastic limit of the solid once you reached over here. Okay, perhaps if you were over here somewhere, you would have come back to zero, but you pushed it too far and now it will have a permanent strain. Okay, so that is what we meant by proportional limit and elastic limit. Okay. So this shows the loading and unloading behavior of a material which is elastic at stress greater than the proportional limit. So even after the linear proportionality is lost, you see over here, so the proportional limit might be somewhere over here and the elastic limit might be somewhere over here. Okay, so the proportionality was lost, say, somewhere over here, and hence you can see this curve over here. So this is what 5.6a is. So figure 5.6a illustrates the loading and unloading behavior of a material which is elastic at stresses greater than the proportional limit. Okay, so it is all elastic in this region. Okay, so and for the material shown in figure 5.5, all these four figures which you have in 5.5, the proportional and elastic limits coincide. So for all these figures, you just observe that these two limits are having the same value. Now please do not mistake that they are the same things. They are not. I mean, they are what their definitions are. It just so happens that these kind of materials which are shown in figure 5.5, for them there is a negligible difference between proportional limit and elastic limit, and hence they are shown or assumed to coincide, but they do mean different things. Okay, so for these materials which you see in figure 5.5, these steels and aluminum and gray cast iron and this polymer which you have, commercial polymethyl methacrylate, for these materials the behavior is something like this, which is plastic. Okay, so it has the slopes of the unloading and reloading curves are nearly equal to the slope of the initial elastic region. So this slope of the initial elastic region is the same as that of this reloading curve. Okay, so what is happening in this experiment? For a plastic behavior, I mean, again, this is a steel or aluminum material, aluminum alloys which you have seen in figure 5.5. You gradually increase the load, okay, and definitely it will keep on, I mean, the proportionality and the elastic limit has definitely been lost all the way. So proportionality is definitely lost over here, and then you can get over with this particular part, and once you arrive, you start unloading, it will fall back to this permanent strain. Now you start applying a load again from this strained position, and that you would get as a reloading curve, and then you take it to this stage. Okay, so this is what you observe over here. Okay, now what they say is that slopes of the unloading and the reloading curves are nearly equal to the slopes of the initial elastic state. So slopes of the unloading, this one, and reloading curves, this one, is nearly the same of the initial elastic region. Okay, So this is normally what is observed, and it is convenient to think of the total strain OB under a given stress as being made up of an elastic part and a plastic part. So the total strain which you see in this case, total strain, okay, let me just remove this, which is OB is equal to strain, elastic part, let me just call it an elastic part. Okay, the strain has two parts, one that is AB and a plastic which is OA. Okay, so that's how we would calculate the elastic and the plastic part. And as you know, I mean, the elastic part is such that, I mean, if you this AB will come back to 0 if you remove the load. That's why, and plastic part will not come back to 0. Okay, so that's how you would see this somewhere over here. So this is the same, say if you would close it down somewhere over here, elastic part, and then you would have that plastic part. Okay, so as you can see from this diagram itself, the plastic part is quite large compared to the elastic part. Okay, so that's something which you are able to see in this diagram as well. Okay, let me just rub this part out. Now, the not so good part about the proportional limit and the elastic limit is that we cannot find them precisely. Before doing this, let's just see how any of this curve is calculated. So let's start with, say, this one. I mean, okay, let's start with, say, any ductile one. Okay, this is good enough, I think. So when you do an experiment, I mean, any experiment which you may have done until now, either at IIT or before this in your schools or whatever, and say you get for a very small strain, you get a graph like this. Just recall, how do you actually get this graph? What you do is you get a certain data point, say over here, over here, over here, over here, okay, and then you draw this best fit curve, okay, which is a line if the strain is very small, and then it can move along in a behavior like this. But the idea is that you have all these data points around you, okay, and this is the best fit curve which you do to find this behavior. So you don't get a continuous curve like this ever in an experiment. And remember, in the first class of this chapter, we had clearly discussed about a macroscopic experiment being done. This is that macroscopic experiment. Okay, so you have this behavior which you see, and this behavior comes out after fitting the curve through all the data points. Obviously, the more data points you have, the better your curve will be, but the data points are always discrete. Okay, this curve which you draw is continuous. Okay, now coming back to the note that neither the proportional nor the elastic limits can be determined precisely. Okay, for they deal with limiting cases of zero deviation from linearity and of no permanent set. So proportional limit, if you recall, is that case where something like this happens. Okay, so there is a linear part, and the deviation which happens from this linearity is what your proportional limit is. Now, how do you calculate that? Okay, one might always say, well, we can calculate the slope of the curve at this point, and then we calculate the slope in the very next point, and if it is the same, then we say, well, it's still linear, so it is within the proportional limit, and it keeps on doing like this. But eventually there will be a point where the next point will have a different slope. Okay, and that point mathematically you can say is the proportional limit. But come back to this sort of method which we have arrived to get to this curve. We have arrived at this curve after the curve fitting, and then how much you are taking this distance, okay, between these points to calculate the slope also matters a lot. So it will all be dependent on how small you can go and how accurate your curve fit is. So that is why people say that you cannot find these two limits, proportional limit and elastic limit, precisely because they deal with the limiting case of zero deviation from linearity. So you want the slope to deviate from this m1 and m1 plus delta m1, but delta m1 must tend to 0. So not equal to 0 but tending to 0. So this is what a proportional limit is mathematically. But in an experimental analysis, as I have said, I mean, it's not precise. Now, why is the elastic limit not precisely defined? It again, it deals with the limiting case of zero deviation, oh sorry, of no permanent set. Okay, meaning you do not get a permanent strain, and that's where you want to say your elastic limit is. So if you have something like this, sorry, so I'm just writing sigma and E assuming that it's all in the x direction only, so I'm missing out the subscript, okay, just because it's easier this way. And there will be a stage in this chapter itself where we'll have to use out the full form of it. So because we are only discussing uniaxial tensile test, I think it is fair enough to ignore the subscripts. Okay, so why cannot the elastic limit be considered as precise? Let's see. You have a load, you increase, and then if you remove the load, it comes back, okay, to zero strain. So permanent permanent set is a permanent strain. In your textbook the word is permanent set, but that means a permanent strain, like even after removing the load it will have a permanent strain. Now you take up another value and come back, it should come back to 0, and so on. And you keep on doing this, okay, you keep on doing these tests. They will not lie on the line, but I'm just drawing it like that. Keep on doing those number of tests. Eventually when you find that you have reached a value after which if you unload the material, I mean, you have to keep on taking a new material, and then you will get back to this point which is not a zero strain, okay, you come back over here. So this is also a limiting case. How is it a limiting case? Because the idea is that the point which you have considered just before this, that point, if you unload from that point, it should come back to 0. Okay, so that is why it is also a limiting case of no permanent strain, and that makes it also harder, again depending on how much distance you are taking between these 2 points. So that is why you cannot be precise about elastic limit. So one of the things which you should notice is that which you should yourself check, why is the word precise used over here, why not accurate? So there's a distinction between precision and accuracy, which you may recall from your earlier courses. Please think about it, that why has the author of your textbook used the word precise and not accurate. Okay, fine. So that is one part of it, that even after having these very clear definitions, in reality in an experimental setup it's not possible to find these values, proportional limit and elastic limit, precisely. Okay. Now, since the plastic deformations of the order of the elastic strains are often unimportant, instead of reporting the elastic limit, it has become a standard practice to report a quantity called the yield strength. So rather than reporting the elastic limit or the proportional limit, we report something called yield strength. And as I have said before, the plastic deformations normally are much larger than the elastic deformations. And I think it's somewhere in your textbook it's written beforehand that it's around 100 times more than the elastic limit. I mean, just an example. So it is fine to ignore that 1% of part of the plastic strain which is of the same order as elastic strain. So you don't have to worry too much about all that, and hence it is okay to find a quantity called a yield strength. So what is yield strength? This is the stress required to produce an arbitrary plastic deformation. Okay. So rather than having this limiting case that there should be no plastic deformation at all, which was required for elastic limit, better get this yield strength. What it does is it is that stress which is required to produce a certain arbitrary plastic deformation. Normally, that percentage of strain is a 0.2%. So this is how you want to do that. At this 0.2%, okay, strain, you draw a line which is parallel to the elastic part of the curve, okay, and then you let it go up. The point at which it meets your curve, consider this 1020 CR, okay, ignore the other curves, okay, consider this 1020 curve. The point at which this line, the slope of which is the same as the elastic part of this arbitrarily defined plastic meets this one, this is the yield strength. Okay, and this is called a 0.2% yield strength because that arbitrary plastic deformation which you have considered is 0.2%. Okay, you can also have a 0.5% yield strength, but 0.2% is what we want to go with over here. So that is done over here. Let's see if there are okay, you have another example where this is done. So you go up, and for this material the yield strength can be found by the intersection of this line with this one. For this material the intersection can be found as this value, and for this material the intersection can be found as over here, so slightly under 400 I would say. Okay, so let's see. Okay, it's not there in the other cases. So that's how you can find the yield strength, and this will be a exact precise number for you. Okay, so there will be no doubt about this one because it's essentially the intersection between two curves. Okay, so they are more sharply defined compared to the proportional limit. Okay, that's what, because it is just the intersection and then there's no limiting limit involved in this case. Okay, so you may do a course in numerical analysis where you will see that taking a limit, I mean taking anything, for example delta x tending to 0, a computer will not be able to do that. What it will can do is, it to its own capacity, it will be taking delta x to whatever small degree you want, and then you can analyze what you do. Okay, so it depends a lot on the user of these methods. Anyways, so yield strength is more widely used, and because they are more sharply defined than the proportional limits which we have seen before. Okay, so this is one of the most important things that will stay with you for a very long time in this course, in definitely in machine design. And you will learn later on that this is seen as a sign of failure. If your stress has reached this particular point, means it has reached failure. Okay, now this does not mean it's the first point where permanent strain will be there. There may be a value which is slightly less than yield strength, which will also give you a permanent strain. But as we have argued before, that strain is of the same order as elastic strain, so we kind of ignore that. I mean, it doesn't bother us much. Okay, so for many of the steels, the plastic deformation begins abruptly, resulting in an increase of strain with no increase, or perhaps even a decrease in stress. For such a material, the yield point is defined as a stress level less than the maximum attainable stress, at which an increase in the strain begins without an upper increase in strength. So let's look at this figure. So we are referring to a material which is a 1020 HR. For these kind of materials, the plastic deformation begins abruptly, resulting in an increase of strain, or with no increase in increase of strain with no increase or perhaps even decrease in stress. So the strain will increase with a decrease in stress. You can see that this curve goes up and then it comes down. So now the strain will increase. In this case, look at this part of the curve. The strain will increase with a decrease in stress. Okay, so that is what is referred to over here. For such materials, for this kind of materials, a yield point is defined as a stress level less than the maximum attainable stress, at which the increase in strain occurs without an increase in stress. So the yield point, okay, not the yield strength, the yield point is an upper yield point at this point and lower yield point for this one. Okay, so we don't have something called yield strength for materials like this, in which there is this abrupt plastic deformation, but rather than having this upper yield point and the lower yield point. So the upper yield point is very sensitive to rate of loading and accidental bending or irregularities. So the lower yield point should be used for design purposes. Now, I have said that if you take a specimen like this and then you have to, in a tensile test, you pull it, and the idea is that you pull it slowly. What has been observed for materials like this, that this value which you get, okay, I mean, once you draw the curve, fit the curve, and this value which you get is very sensitive to the rate of this loading. Okay, I mean, you want to do it slowly, but your machine must have a number, how slow, and hence it changes a lot every time with, if even if you slightly vary this pulling up rate. And that is not good. In the sense, it is not good because it should be a material property. A material property depends on the material, not how you load or what dimensions you take and so and so that is why it's not a good idea to use this one. Okay, and only the lower yield point, which is not as sensitive to the rate of loading and other testing conditions, is what is used in design purposes. And as I've said, I mean, yield strength and yield point are used for designing. The failure theories assume that if yield point or yield strength has been reached, then failure has happened. So there you don't design, I mean, you don't want it to be used beyond that point. So lower yield point is used. Okay, this is what should happen. Unfortunately, It is the upper yield point which is often tabulated without being labeled as such in tables of properties. Now there are properties where the materials are defined. For example, you will have aluminum, you will have steel, and you will have, say, magnesium, some sort of sorry, aluminum, steel, and some other variation of it. Okay, say cast iron, and then you will have yield point which is written. So the tables which tell you, I mean, someone else somewhere has done these tests, and there are these design tables where these values are available. Those tabulated values which we use in designing are actually the upper yield values. So it's not specified that it's the upper yield value in the table, but that is the case. Okay. So that is what they say by saying that unfortunately it is the upper yield point which is often tabulated without being labeled as such in the tables of properties. So you must be careful about it. Okay. I mean, you should know this different. You should know what is right, what is wrong, and then get used to the real world where actually the tabulated values are the upper yield point. Okay. Okay. So let's stop this discussion at this point, and we will continue with the next paragraph in our next class. Okay. So thank you.